Good morning again, everybody. I wrote here a reminder of the important things we saw last time, and they're really important. These are very, very useful and important results in this course. So the first was the fundamental theorem of calculus, which said the following. If we have a continuous function, and it's important that it's continuous, and we define big F to be the integral from a to x of little f, this was the function that accumulates area under the graph of f, intuitively speaking, then it turns out that this function, this accumulating area function, is differentiable, and it turns out to be an antiderivative of little f. Its derivative is little f. Before I remind you of the corollaries, I want to mention one thing. I tried to avoid it until now because from my experience it's kind of confusing, but it does appear everywhere you'll see this theorem written, and so it's important to eventually throw it in. So the way you'll usually see this written is the integral from a to x, and here this is kind of shorthand for writing f of x dx, right? But in order to emphasize that this capital F depends on x, where x is only the upper bound of the integral, and the x that would sit here is only the variable of integration, which makes no difference, the way it's usually written is f of t dt. This t, which you can call x, or you can call y, or you can call whatever you want, is not important. The integral, whenever you fix an x, the integral from a to a fixed number, call it b for a second, of a function, does not depend on what you call the variable of integration. Is that clear? Are there any questions? So it's customary to write this f of t dt in order to emphasize, in order to make it really clear that this function depends on the upper bound of the integral, and everything else is fixed. Okay, f is fixed, a is fixed. You change x, you get a different value for capital F. Okay? Okay. Now, the corollaries were, the first one was, every continuous function has an antiderivative. There it is. It's this function. Although, and we mentioned that antiderivative does not necessarily have an explicit formula. Sometimes it does and sometimes it doesn't. Okay? And the second, which is maybe the most useful formula in this course, is what we call the Newton-Leibniz formula, and we proved how it follows from the fundamental theorem. And namely, it says, if you have an antiderivative, not necessarily this, any antiderivative, then calculating the definite integral is easy. You just plug in the antiderivative, evaluate it at b, subtract its value at a. Okay? And the way to find an antiderivative is, of course, not this, because this is non-explicit. The way to find it is to do an indefinite integral, like we did in the previous week, using all the various methods. So once you come up with an antiderivative, you can calculate the definite integral easily. We did one example. We're going to do more examples today and in the future. But the idea is very, very simple. And I'm sure you've done this before in your previous studies. Okay. Any questions on this? Is this clear? Okay. So moving on, I want to first show you, so this is so standard that we're going to do it so many times, and it's going to be like kind of we're going to work on examples and eventually get to this step where all we need to do is find the antiderivative, and that's going to be kind of that's going to be the easy part. Once we got here, we're safe. We're there. We're done. What I want to show you first is an example of using this fundamental theorem not in this context, in a different application. Okay, so example. Suppose we want to calculate a limit the limit as x goes to 0 of 1 over x to the power 3 times the integral from 0 to x of sine squared of 3t dt. You want to calculate this limit. So we look at it, we freak out, right? Okay. Then we do this. Now you're good. And now we say, okay, we can handle this. Why can we handle this? Why is it not that scary? Well, we're not going to first evaluate this integral, then plug x, and then solve it. We're going to do something different. We're going to rewrite this, and this is not a deep move. We're going to rewrite this as a quotient, where down here we have x cubed, and up here we have this integral. Integral from 0 to x. Integral from 0 to x, sine squared of 3t dt. Do you agree that these are the same thing? Okay. Now let's see what we have here. As x approaches 0, the denominator clearly goes to 0, right? What about the numerator? As x approaches 0, this is the limit of this thing is the integral from 0 to 0, which is what? 0 independent of what the function is, right? So this is a 0 over 0 situation. Do you recognize that? And what can we do in 0 over 0 situations? We can do l'hôpital. So let's lop it. Good. I like that. So l'hôpital, how did we write it? LH. L'hôpital, 0 over 0. So what does l'hôpital tell us? L'hôpital tells us, take the derivative of the top and the derivative of the bottom and do the limit. If it exists, it equals the limit of the original quotient. So what we get here is the limit. X goes to 0. I get to choose first. I do the bottom. Your turn. Right. Very good. So the derivative of the top is not that scary. It's the derivative of a function. This is a function of x. Remember, this t is just the variable of integration. The entire top is a function of x. And its derivative, by the fundamental theorem of calculus, is just the function that sits inside. Sine squared of 3x. And this follows from the fundamental theorem of calculus. That you're using the fundamental theorem? Yes, you have to mention it, of course. Anytime you use a theorem, you have to mention it. And moreover, every time you use a theorem, you have to verify that its conditions hold. What are the conditions of the fundamental theorem? It's on the board. What are the conditions? Right, the function in the integrand, the function inside the snake, has to be a continuous function. And in this case, it is. Sine square is a continuous function. Clear?
How did you get sine squared 3x?
It's just the function inside. Let's look back at this board. That's the fundamental theorem. If you have an integral from a constant to x of a function, where this function is continuous, please look on this board. Hello, I'm here. Hello? Thank you. If you have an integral of a continuous function, that's your big F, its derivative is just what sits inside. That's precisely this theorem. Clear? Everybody? Okay. So back here, we get this limit, and that's it. The snake is gone. We just have to calculate this limit. How do we do this? Well, it's very tempting to say sine of 3x over 3x goes to 1, right? But it's not precise, right? There's a sine squared of 3x, and there's only 3x squared. So what do we want to do? We want to multiply this by 3. Now we have 3x times 3x, But if we multiply this by 3, we have to multiply the top by 3 as well, right? And now we have here sine of 3x over 3x. Two of these, they go to 1. Hence, the limit is what? Very good. Questions on this example? Okay. So, this is one instance where we're using the fundamental theorem not as it appears in the Newton-Leibniz formula. Let's do another example of a situation like that. So let's call this example 1. Example 2, suppose we define, so let's call it g of x equals the integral from 0 to x plus x squared of sine of t dt. Okay, so this is g of x. And without being too sophisticated, find g prime of x. That's it. So can we say that the derivative is just the function sitting inside?
No.
Well, we can say that, but that won't be true, right? Because the fundamental theorem tells us if the upper bound were just x, then it would be true, then it would be just a straightforward application of the fundamental theorem. Do you agree? Okay. So what can we do? How do we handle, right, there's a certain chain rule hidden here. So let's see how that happens. So we know by the fundamental theorem of calculus that for f of x equals the integral from 0 just to x of sine of t dt, f prime of x equals just the function sitting inside. This is precisely the fundamental theorem, right? And this is true because the function sitting inside is a continuous function. Good? How does g, which is the function we want to find the derivative of, how does g relate to f? What's the relation between g and f? So note that there's a composition there, right? No, not plus. No. Exactly. G of x is precisely f of x plus x squared. Very good. Look at this a second. Do you agree? G of x is the integral of sine from 0 to this value. F of this value is plugging this here, is the same thing as the integral from 0 to this of sine. It's precisely g of x. Does everybody agree? Does everybody see this? Yep? Okay. So now, if we want the derivative of g, that's what we're asked to find. It's going to be taking the derivative of this, and this is a composition. Taking the derivative is a chain rule. So, therefore, g prime of x equals f prime at this value, x plus x squared, times the inner derivative. What's the inner derivative here? Times 1 plus 2x. And now, what is f prime at this value? This we know. F prime is just sine. So this equals sine of x plus x squared times 1 plus 2x. Questions? I can see in some people's eyes that they're with me and they followed and they got it, and some people are just in total awe. questions? Ask. No? Okay. Now, you can do similar things if, for example, instead of 0, you have here a function of x as well. What would you do? Well, you can break it into two integrals, one from 0 to the top and the other from whatever the function is to 0. And then for each one, do a reasoning like this. Okay? Or you can actually set this up as a theorem if you want. You can say that the derivative of the integral from one function of x to the second function of x would be the function sitting inside evaluated at the top times the derivative of the top minus the function sitting inside evaluated at the bottom times the derivative of the bottom. Okay, and a proof of it would be using just these sort of arguments. Okay, I prefer not to remember that as a theorem, because if you got the idea of what's going on here, it's very easy to do it without remembering theorems, just remembering what you need to do. And it's not any more work. And it's better not to memorize theorems. It's better to understand what's going on. Okay? And use your understanding rather than your memory. Because memory is something you tend to forget. But once you understand something, it's harder to forget it. Okay, so these are two examples of using the fundamental theorem of calculus directly. And before we move on to more uses of the Newton-Leibniz theorem and more calculations of integrals, which is the most useful application of this, I want to also make a little remark. So, the fundamental theorem of calculus tells us there's a very deep connection between antiderivatives on the one hand and definite integrals on the other hand. So these integrals, which intuitively are areas under graphs, are related to antiderivatives. Okay? And I want to ask you, how far does this relationship go? How deep is this relationship? So, for example, is it true that if f is integrable, whenever we say integrable, we mean in the Riemann integrable sense, that it has that area under the graph, the Riemann sums converge. Okay? Then, or let's write this as, let me rewrite it. Instead of if then, I'm going to write f is integrable implies f has an antiderivative. Is this true? Is this a theorem? Does every integrable function have an antiderivative? If you want to argue that it's true, give me the line of argument, not the precise proof, but what the idea is. If you want to argue that it's false, all you need to do is give me a counter example. Okay? That's the way you negotiate correctness of theorems. If they're true, you have to prove them. It's sometimes harder. If they're false, all you need to do is give a counter example. So does anybody have an idea how to approach this?
It's not true.
You're saying it's not true. Well, convince us. Give us a counter example.
We said that functions can be integral, but their antiderivative be a non-elementary function or even not to have a formula.
So you're saying a function can be integrable.
Its antiderivative not be a function, be a something.
So we said that an antiderivative sometimes doesn't have an explicit form, is not an elementary function. But once we say it exists, then that satisfies this. It exists, even if you don't know a formula for it. So that's not a direction, or that that wouldn't come up with a counterexample. Yes?
According to the corollary that you wrote down there, every continuous function has an antiderivative.
That's true.
Every continuous function is also integrable.
Right.
We had from a theory before, therefore it has to have an antiderivative.
So what you're saying is every continuous function is integrable, true, has an antiderivative by the corollary to the fundamental theorem, true. So you won't be able to find counterexamples for this using continuous functions. That I agree. Continuous functions satisfy this. But that's still not a proof that every integrable function, maybe not necessarily continuous, hint, hint, has an antiderivative. Okay, so here's a counterexample. This is false. This is not true. Not every integrable function has an antiderivative. And a counterexample, well, just take a non-continuous function. That was a good observation that for continuous functions it is true. But if you take a non-continuous function, and we even did a similar argument when we first talked about antiderivatives, here's a non-continuous function. Let's say the function which is 0 between -1 and 0, and then it's 1 between 0 and 1. So this is little f. It's not a continuous function. It's still integrable because it's piecewise continuous, for example. Do you agree? Okay, you can talk about the area under the graph, and that's easy. The area here is 0 plus the area here, which is, in this case, just 1. Do you agree? Does everybody agree that this is an integrable function? Yes? But we argued, this was our kind of our first example of a function that doesn't have an antiderivative, that this function does not have an antiderivative on the entire interval. At 0, whatever candidate you try to take would not be differentiable. Okay? That's one way to argue it. Another way to argue it was to say that this function has a jump discontinuity, therefore it cannot be a derivative of something. Remember those kind of arguments? Remember we actually did this example? Okay, so this function, this f, integrable, has no antiderivative on -1, 1. 0 poses a problem. Clear? So you have to be careful. Just being integrable doesn't guarantee having an antiderivative. Being continuous does. That's the corollary. What if we try the other direction? So call this 1. What if we try the other direction? Is it true that if f has an antiderivative, then f is integrable? Again, integrable in the Riemann sense, in the definite integral sense, having those Riemann sums converge. Is it true that having an antiderivative guarantees being integrable? You're saying no. If you're saying no, you have to give a counterexample.
1 over x.
1 over x. On which interval?
-1 to 1.
Okay, 1 over x on -1 to 1. So you're saying it has an antiderivative. Why?
It's out of x.
But not at 0. At 0 we have a problem, right?
Yeah.
That would actually work. What your example would actually work, but you have to be careful with the interval. So okay, so you you got the idea, I think. Let's write it. So this again is not true. Okay? And a counterexample, so this was a counterexample. And there's a counterexample here too. And the idea is that saying that a function has I'm sorry. Saying that a function has an antiderivative does not necessarily mean that it's a bounded function. Okay? A function can be not bounded and have an antiderivative. Whereas saying that a function is integrable necessarily means that it's a bounded function. We only defined integrals for bounded functions. You cannot throw that into the definition, but then it follows. You can prove that it must hold. So being integrable implies being bounded. It's built in. So a counterexample would be, for example, what you suggested, maybe the function 1 over x, let's say on 0, 1 on the open interval. So this function, 1 over x, this function has an antiderivative on 0, 1. What's the antiderivative? Right. So antiderivative on 0, 1 open is ln of x. 1 over x is just the derivative of ln of x. But it's not integrable on this interval because it's not bounded. Okay? So it has an antiderivative, but not integrable since not bounded. Okay? So both directions of what would be a reasonable thing to assume in light of the fundamental theorem are wrong. Just being integrable does not imply having an antiderivative, and having an antiderivative does not imply being integrable. You have to be more careful with these sorts of arguments. Okay? And the way they're written here, it's, straightforward and very clear in the counterexamples, but sometimes these sort of arguments hide in trying to prove or argue more general things, and you kind of say, it's integrable, so we have an big F and continue, but that's not necessarily true. You have to be careful with these things. It's more delicate. Okay? You can only say as far as the actual statement of the fundamental theorem. Yes?
So the fundamental theorem just says that if small f of x is integrable and is the same as the antiderivative.
No. The fundamental theorem in the assumption parts has that little f must be continuous. Okay? If you don't require continuity here, this is not true. The only thing you can say, and we actually said that was the theorem preceding this theorem, is that this f, you can still define it. Okay? If it's integrable, this is well defined, but all you can say about it is that big F is going to be continuous. It's not necessarily going to be differentiable, and of course it's not necessarily going to be an antiderivative of little f. Okay? So this is essential, and we even saw where the role of continuity is used in the proof. We even saw that. Okay, so maybe there's a different proof, but there isn't. Okay, so that proof you can see where it will collapse if you don't require continuity. And in fact, this is essential for this statement. Okay, so only for continuous functions is this true, and everything follows. And here you can be a bit more liberal. You can say that f is integrable. You can say that f is an antiderivative of an integrable function, and I think that's sufficient. But I think we phrased it also for for continuous. Little f. Hey, 1 second. I want to sip water. For some reason, I'm coughing here. Yes, question.
Yeah. Can we take infinity or negative infinity as one of the bounds?
So the question was, can we take infinity or negative infinity here? Here is one of the bounds. We haven't defined that yet. It's going to come. Okay, those are called improper integrals. Okay, and we're not there yet. For us, the intervals were always finite intervals, a, b. Okay, we will get there, but not yet. Okay, good. So now let's go back to calculating after making all these examples and remarks. I want to go back to just calculating definite integrals. And now at our disposal, finally, after waiting patiently for quite a long time, we finally have the Newton-Leibniz formula, and we finally can actually do calculations. But there are more tools for doing calculations, and I want to show you them. So I'll state them as theorems. So the first one would be integration by parts for definite integrals. We saw integration by parts. We saw this theorem for indefinite integrals. It has a counterpart for definite integrals. So if u and v have continuous derivatives on AB, so we're assuming that they're differentiable and that the derivatives are continuous. Okay, so it's a bit stronger than just being differentiable. Okay, it's a bit stronger. So if these two functions have continuous derivatives on AB, then, and this is the definite version of integration by parts. So the integral from A to B, definite integral, of uv prime equals uv evaluated between A and B minus the integral from A to B of u prime v. That's the formula. It follows from the product rule for derivatives in exactly the same way as the formula for indefinite integrals follows. Okay, maybe let's do it. Let's write the proof. So we know that uv prime, we know that if we take a product prime, that equals uv prime plus u prime v. This is the product rule for derivatives, right? Remember, u and v are functions here. Now what we're assuming here, that these functions have continuous derivatives. So u prime and v prime exist, and they're continuous. So in particular, u and v themselves are continuous, because they're differentiable. So everything in this line is continuous functions. Do you agree? It's products of continuous functions. Does everybody agree? And since they're continuous, we can integrate them. In the definite sense, they're integrable. Every continuous function is integrable. So I'm going to put snakes on everything. So we have the integral from A to B. This is the definite integral of uv prime equals the integral from A to B of uv prime plus the integral from A to B of u prime v. So this is legitimate since we know that everything is continuous by assumption. And now, what is the definite integral? Definite integral of uv prime. The definite. We're doing definite integrals. Exactly. Why?
Because due to the fundamental theorem of calculus, you can...
Don't argue it again. It's the corollary. Right? It's Newton-Leibniz. If you have the definite integral of a function for which you know the antiderivative, and you know the antiderivative of uv prime, right? What's the antiderivative of uv prime? It's just uv, right? So this is the antiderivative, that's the capital F, evaluated between A and B. So here I just used Newton-Leibniz. Do you agree? And now all you need to do is move one of them. Which one? UV prime. Move this to this side, and you get this formula. Good? So this completes the proof. Questions? So now, if somebody gives me a definite integral and tells me, okay, calculate the definite integral of blah, I have two choices. Either I can find the antiderivative first in all the methods that I had before for finding antiderivatives, and then do Newton-Leibniz. Or I can do all kind of moves and steps involving definite integrals, like this step, for example, and only then use Newton-Leibniz. Okay, so let's do an example. So suppose I want to calculate suppose I want to calculate the integral from 0 to pi, definite integral, of the function x sine x dx. Jeffy, you do this with Riemann sums like last time, okay? Go. Okay, so we're going to do it in more sophisticated ways. Don't do it, right? No. Just a joke. Okay, so this really calls for integration by parts. You should, that you should already feel at this time. Then when you see a product of two functions, this kind of yells out to you, hey, integrate me by parts. Right? Does everybody see that? Okay, so let's do it using the integration by part theorem for definite integrals. So what does it tell me? Well, I have to decide the u prime and the v again, so, or the u and the v prime. So I took this to be u and this to be v prime. So u prime is 1, and v is what? Minus cosine of x. Does everybody agree? And now the integration by parts formula tells me, please always write this. Always write this. Never be lazy. Write this. So what do I get? I get u times v, so minus x cosine x, evaluated between 0 and pi, right? Minus the integral of u prime v. So u prime is 1, v is minus cosine x, so this becomes a plus, and I get cosine x dx between 0 and pi. Good? Now, so here I just plug in the values. Remember, this is just notation for plugging in pi minus plugging in 0. That's just notation. So it's minus pi times cosine of pi. What's cosine of pi? Minus 1. So it's minus pi times minus 1. So it's pi. Right? Minus this thing evaluated at 0. So minus minus makes it a plus, but when we plug in 0, it's just 0. Right? And then I have this integral to solve. And how do I solve this integral? Wait, how do I solve it before what the solution is? Newton-Leibniz again, right? I find the antiderivative, so I'm going to write plus the antiderivative, which is sine of x, evaluated at pi minus evaluated at 0. So here I used Newton-Leibniz. Do you agree? Everybody? Good. So what do I get? Well, sine of pi is 0, sine of 0 is 0, so in fact this factor doesn't contribute anything, and the answer is just pi. And it better be a number. Remember, a definite integral is a number. If you somehow got x's here, oops, you're doing something wrong. And that happens if you somehow forget to put the bounds and just mix up antiderivatives and definite integrals. No x's, it's a number. Good? Okay. So we have two options. Two options. Maybe I'll just write this. So when you're given and asked to calculate a definite integral, you have two options. One, find the antiderivative using all the ways and different methods that we've learned previously, and then do a one-time Newton-Leibniz thing. So, remark, two methods, and they're very similar. If you do one way or the other, you're going to basically be doing kind of the same things. Okay? Two methods to solve definite integrals. Method A, find an antiderivative and then use Newton-Leibniz. Is it clear what I mean by A? Okay. B, use theorems or methods or whatever for definite integrals to simplify and only then use Newton-Leibniz, and only at the end use Newton-Leibniz. So in the previous example, which of the two methods did we apply? B, exactly. What we did here was we took the definite integral, we used the theorem for definite integrals in order to get here, and we simplified it. Now the integral is real easy, and only at the end we actually used Newton-Leibniz when this step was already an immediate integral. Okay? The other way to solve this would be to do a side calculation completely separately of solving just this, the indefinite integral, finding the antiderivative of x sine x, which, by the way, how would you do? Right, you would do integration by parts for indefinite integrals, right? So find the antiderivative of x sine x, and then plug in pi minus plug in 0. Okay? So homework, solve this by first finding an antiderivative of x sine x. It's not going to be harder. There's a conservation of difficulty rule governing this. Okay, you're basically going to do very similar things. You're going to do integration by parts. It's going to look like that. Then you're going to plug it. Okay? But it's important to... What's really important is not just to be able to tell that there are two different methods and to apply them correctly, but not to have them mixed up. And what people many times do, and that's wrong, and that actually leads to wrong answers, is to start doing this, but then forget to write this, and kind of convert en route to doing indefinite integrals, and getting everything confused, and then they get x's in the answer, and they don't understand what's going on. And it's important to do either this or that, and to write it correctly. If you're doing moves, definite integral moves, then this is fine. If you're doing the indefinite integral, it's a side calculation. It's not equal to this. It's a side calculation, and then you plug it in. Clear? Everybody? Okay. So this was the integration by parts theorem for definite integrals. Let's write the substitution formula for definite integrals. It's again going to resemble the substitution formula, the change of variables formula for indefinite integrals, but there's going to be a twist, and it's going to be slightly more confusing, but just a bit. So theorem, substitution or change of variables, substitution. So let f from AB to R, bear with me with a formal statement of the theorem, and then we'll see an example which will be clearer than the formal statement. Let f from AB to R be continuous. And let phi be a function from alpha beta to a b. So phi is a function that goes from some interval alpha beta to the interval ab where f is defined. Okay? And let phi, like this, be differentiable. Such that, so it has to satisfy that phi of alpha is A and phi of beta is B. So the endpoints go to endpoints. Then, and this is the formula, the integral of f, the definite integral of f from A to B, equals the integral, just like before, of f of phi of t times phi prime of t dt. Remember, this is what we had for indefinite integrals? But now there are bounds. Now it's a definite integral, and it goes from alpha to beta. Okay? So let's do an example before you panic. And there really is no reason to panic. You'll see in the example that it's really exactly the same idea as before. You just have to take care of the bounds here. I don't think we did. I'm not going to prove it now because it's a bit confusing, and I don't think I proved the indefinite version either. But I did say that this is just like the integration by parts is the dual of the product rule. This is precisely the dual of the chain rule for derivatives. Precisely. Okay. If you're interested in seeing the proof, I would be happy to show it, but I don't want to do it now. Okay. And you can see also that here's the composition, right? F of phi of t. That's why it's obvious that phi has to take values in the domain of f, right? Phi. So these are the t's. The t's live here. T belongs to this interval, and the x's live here. X belongs to this interval. Okay, so phi takes t's to x's, and then you can apply f. Okay, let's do an example. Let's do an example. Maybe I'll start the example down here, where I have the formula, so we can compare them right away without looking at different boards, and then I'll continue it there. So suppose I want to evaluate the integral from 0 to 1 of the root of 1 minus x squared dx. Method number 1, which I didn't even mention in the last remark, is trying to tackle this with Riemann sum. Riemann sums. Don't do that, right? Not a good idea. Method number A, which I mentioned there, forget the bounds, do a side calculation, find an antiderivative for this, and then plug in 1 minus plug in 0. That would be method A. Right? Everybody? Okay. I want to do it using method B, which is first simplify this in the realm of definite integrals, and only after it's nice and easy, do a final touch of Newton-Leibniz to solve it. Okay? So how am I going to simplify this? Well, if you've practiced enough integrals, and it's crucial in this context to do a lot of practice, I said that more than once, then, right, very good. So this calls for a substitution, and it actually calls for a very specific substitution. And inventing it, guessing it for the first time is not trivial. Okay? Only after you think about it for a while, or after you've seen enough of these and you know, I know what to do with this. That's where you should be at this time. So what to do with this is, we want to do a substitution, x equals, you'll see why in a second if you haven't seen this before. So you can choose either sine or cosine. I'm going to choose cosine. Cosine of t. So remember, we wrote it using a long equal sign, and everything underneath is the blah blah that just justifies this theorem. So I'm going to take x to be cosine of t, and in this case, what is dx minus sine of t dt? Do you agree? So this is the substitution that I'm doing. But now careful, I'm doing a definite integral. So what do I get on this side? I get the snake. Here's the snake. Here what do I get? And this is the reason I chose this substitution. I get 1 minus cosine squared of t. Do you see that? What's 1 minus cosine squared? Sine squared. What's the root of sine squared? Sine. Do you agree? You're right, it's the absolute value, but if we're only between 0 and 1, we actually don't need the absolute value because it's positive. But that was a good observation. Good? So do I need to write those intermediate steps, or did everybody follow? X is cosine t, x squared is cosine squared, 1 minus cosine squared is sine squared, the root of sine squared, well, it's absolute value, but on 0, 1, it's positive. So all of this just becomes sine t. And dx is minus sine t dt. So we get 1 sine from here and 1 sine from all of this. So we get minus out here, and then we have sine square of t dt. Good? Almost. We're not done. What did we not do yet? Right. We didn't transfer the limits. And that's crucial when doing substitution at the level of the definite integral.
Can you just leave like that? Go to the end until you find the substitution?
How, what? Say that again?
Can you go on until you find, until you substitute back t for x, and then just plug in the boundary?
Okay, so the question was, can I not substitute the limits? Go on.
At the end.
Right. That would be incorrect. Okay? Why? Because you're saying this, which is a number, equals this, which is a family of functions. And it doesn't make sense. It's not that it doesn't make sense, it's nonsense. Okay? You can't do that. What you can do, as I said, you can forget this a second. Do just the indefinite integral, Then it's fine, and at the end, plug back. But you can't say this equals this, forget the limits, and then at some point where you feel like it, plug them back. You may even get a correct answer. You may even get a correct answer, but no points, at least not for me. It's wrong. Okay, clear? Everybody, this was a very important question. Everybody good? You can't mix the two methods. You can't just go back and forth at will. It's incorrect. This is a number. That's a family of functions. Okay? So we need to transfer the limits. And how do we transfer them? What is alpha? Alpha satisfies that phi of alpha has to equal a. What is phi here? Phi is cosine. This is phi of t. Let's emphasize this. So this is our phi of t. This is phi of t. This cosine here. Do you agree? And f of phi of t was plugging cosine into here. That's this. So phi of whatever I'm going to write down here, that's the alpha. Phi of alpha has to be 0. Meaning cosine of whatever I'm going to write here has to be 0. So cosine of what equals 0? Pi over 2, for example. So here I'm going to write in the bottom pi over 2. And phi of beta has to equal 1. Phi of beta has to equal b. Phi of beta equals b. So phi, cosine of whatever I'm going to write here, has to be 1. Cosine of what is 1?
No, 0.
0, for example. I'm not saying this is the only choice. You can make other choices here.
So, do we have to swap them now?
Wait, we're going to do that. That's going to be the next step. But is this clear? Okay, so what confuses people is many times is how to find these alpha and beta. So the way to find them is your substitution, your function. When you plug in this, you have to get this. When x equals 0, cosine of this has to be 0. Clear?
I'm thinking about beta is greater than alpha.
Say that again.
Are we saying from let phi be the integral of alpha to beta? That beta is
Okay, so you're saying this interval is... Okay, so when we... You're right, you can make different choices here and make alpha greater than beta. I didn't pay attention to that, but that's still okay. Because remember, when we defined the integral from alpha to beta, we said there's something artificial in putting the alpha on the bottom, beta on the top. It's the area under the graph, and it doesn't depend on which way you look at it. And then we said, by definition, we're going to define if beta happens to be less than alpha, the integral from beta to alpha is just going to be minus the integral from alpha to beta. Definition. Remember we said that? And that's kind of what we're doing here. And that's going to be the next step, which this really calls for. Okay? So it's okay. It's legitimate. Okay. Maybe not as a first example. Maybe I should have chosen, but that's okay. Okay. So once we're here, we can continue this calculation. So what do we get? And note, we're still at the level of the definite integral. We're still doing definite integral moves. Okay? So I'm going to swap these at the expense of adding a minus, which would just cancel this minus. Okay? So this equals the integral from 0 to pi over 2 of sine squared of t dt. By the way, will I need to go back to the original variable?
yeah.
No. No. Why not? What is this thing? It's a number. And the statement of the theorem is that the number I was looking for, namely this number, equals the number I'm going to get here. That's the statement of the theorem. There's no need to go back to the original variable. Okay, I'm actually going to get a number once I finish that calculation. Clear?
Why did you get out the minus again? The minus?
I said minus the integral from this to this is swapping them. That's the definition. Okay. So what's the integral of sine squared? Again, if it's the first time you're seeing the integral of sine squared, it may take you a while to figure out how to beat this thing. But you should be eventually, hopefully already, but if not, then eventually, at the point where this is something you know how to do. This is something you've seen before. Okay? And the way to do this is to use a trig formula. So this equals the integral from 0 to pi over 2 of 1/2 1 minus cosine of 2t. That's the standard way to... This is just a trig formula for sine squared. Okay? And once you get to this point, now I'm finally going to use Newton-Leibniz. Now it's simplified enough that I can just find the antiderivative as an immediate integral and be done with it. So I get this 1/2 sitting out here. What's the antiderivative of 1? T. Minus. What's the antiderivative of cosine of 2t? Sine of 2t. But wait, the derivative of sine of 2t is cosine of 2t times the inner derivative 2, which I don't want, so I'm going to add a 1/2 here. So this is the antiderivative, and it was an immediate antiderivative, evaluated between 0 and pi over 2. This is Newton-Leibniz. And when you get to this step, usually it's the step where you're already doing a sigh of relief. I solved it. This is the easy step. This is something that's already, we know how to do. Okay? So now it's just plugging in values. So what do I get? I get pi over 2 from here divided by 2, so that's pi over 4. If I plug in pi over 2 here, I get sine of pi, which is 0, so it doesn't contribute anything. Minus, and then plugging in 0 gives nothing. So the final answer is actually pi over 4. Questions? It would be good practice to try and solve this using what we called method A, to try and find the antiderivative of root of 1 minus x squared in terms of x, finding the antiderivative. The way to do that is do a change of variables at the indefinite integral level as a side calculation, and then do Newton-Leibniz directly on that. Okay? Good practice. Please do it. But don't mix up the methods. Never ever. Big no-no. Questions? Okay. So at this point, I think it's a good time for a break. What we're going to do after the break is show some applications of definite integrals to various things, purely mathematical and from other subjects. So let's have a 10-minute break.